The purpose of this video is to discuss trigonometry of right triangles. So far we discussed the values of trigonometric functions over or inside the unit circle, or somehow related to unit circle. Now we're discussing how to find the values of trigonometric functions using triangles or similar triangles. And so the first thing is the notation. If you have a right triangle like this, and this is the right angle, and you want to find the trigonometric functions for theta, and then theta would being this angle, then notice that the side that is facing the right triangle, the biggest side, is going to be called hypotenuse. We also show it with an H. The side that is adjacent next to, beside the hypotenuse, that is adjacent to theta, is called adjacent. And the side that is facing theta is going to be called opposite. Now, trigonometric functions for this are as follows. Sine of theta is equal to opposite over hypotenuse. Opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. Tangent theta is equal to opposite over adjacent. Cotangent theta is equal to adjacent over opposite. And people have ways of memorizing this. This is SOH. SOH. This one is CAH. This one is TOA. This one is CAO. So what is that good for? First of all, one thing that I want you to notice is that since any right triangle that has an angle equal to the theta is going to be similar to this triangle, it doesn't matter, it's this one, the finding these ratios is not related to the size of the triangle, because they're all similar, and these are just ratios of two sides of the two similar triangles. The two corresponding sides are going to be the same anyway. The next thing is I'd like to do a few examples on the that are related to these formulas. Let's say this is the example one, and here I'm planning to find the values, the trigonometric values for t. So plan is to find sine of t, cosine of t, tan of t, cotan of t. Now, looking at the values, the side that is adjacent to t is this one. This one is the hypotenuse, and this one is the opposite. I do have two of the three sides, and the other part that the side that I don't know, I can use the Pythagorean theorem to solve for. So the first thing for this question is to use the Pythagorean theorem. Use Pythagorean. and that is 15 to power 2 is equal to 12 to power 2 plus opposite to power 2. And when you solve, it's 225 equal to 144 plus O squared. And then that gives you O squared is equal to 81. So O is equal to 9. So this one equal to 9. Now, and sine of t is supposed to be opposite over hypotenuse. Opposite is 9 divided by hypotenuse, which is 15. You can simplify that to 3 over 5. Now, cosine of t is adjacent over hypotenuse. That's 12 divided by 15. That is 4 divided by 5. Tangent of t is equal to tangent of t and cotangent of t. Tangent of t is equal to opposite over adjacent. That is 9 over 12, which is 3/4. Then cotangent of t is going to be equal to the adjacent divided by opposite, and that's 4 over 3. Or I could have used the quotient identities to figure this two out. I can find the secant of t by, and I know secant of t has to have the same denominator as tangent of t, so it's 1 over cosine. So secant of t is 5 over 4. And cosecant t is equal to the again, another quotient identity is 5 over 3. So the next example is to find the trigonometric values for S in the same triangle. This time, the side next to S beside the hypotenuse is this side, and this one is the opposite. And A is, again, by Pythagorean theorem, is 9. Now, when I'm finding values, again, sine of S is going to be, this time, the opposite is 12 divided by hypotenuse. It's going to be 4/5. The cosine of S is going to be the adjacent divided by hypotenuse, that's the 3/5. Secant of S is just the inverse of that one by the identity, and inverse of this one by the identity. Tangent of S is the opposite over adjacent, which is 12 divided by 9, and that is 4/3. Cotangent of S is the inverse of that. And you can compare these values to these values. Here, the sine and cosine of t, they switched when they became for sine of S and cosine of S. So basically, sine of S is equal to the cosine of t, which is the cofunction of sine for t, and then the other way around. And also for tan and for cotan and for secant and cosecant. The values here are the values for S are equal to the cofunctions of them in T. And that's actually an identity, and it's always true for the two angles that make 90 degrees or pi half. The last questions that I want to do is this one. Example. Find the values for theta over here. In here again I have the opposite is given, opposite and adjacent are given. Use another Pythagorean theorem. And that is 10 to power 2 plus 24 to power 2 is equal to hypotenuse to power 2. 10 to power 2 is 100, and 24 to power 2 is 576. So h to power 2 is equal to 676. That is, h is going to be equal to 26. Okay. Now, sine of theta is the opposite over the hypotenuse. 24 divided by 13, which is 12 divided by 26, which is 12 divided by 13. Cosine theta is 10 divided by 26. And tan theta is 12 divided by 13. Cotan theta is equal to 13 divided by 12. So these examples had one thing in common. Some of the sides were given, and we found the trigonometric functions for theta. And the other way around, the other type of examples is that when the trigonometric function or the angles are given and one of the sides is given, then you can find the other sides of the triangle. And we need some practice over those as well.